Good morning, everyone. I am Anwar Srivastav, a PhD student at Department of Engineering, University of Naples, Partenope, Italy. I work under supervision of Professor Agostino Yadishico and Professor Stefania Campopiano, along with my colleague Flavio Esposto, who is a postdoctoral research fellow. First of all, I would like to convey my deep gratitude to these school organizers for giving me a chance to present my research work here. So the work entitled here is the long period fiber gratings in specialty optical fibers. Specialty optical fibers are usually understood as optical fibers which have at least one special property distinguishing them from standard fibers. However, there is no universally accepted definition of the term standard fiber. Actually, we may regard a standard fiber as a simple step index fiber made with a standard material in place of glass fiber silica and with some common values of parameters like the core size and numerical aperture. So apart from standard fiber which we use, we inclined our focus towards specialty fibers because they are application specific and many times a unique purpose used in diverse application which may require optimal flexibility, environmental and temperature resistance, non-traditional operating wavelength, and ability to transmit high power laser energy. Actually, we can group to some category. We can categorize some specialty fibers. Like some fibers use non-standard materials. For example, there are fluoride fibers which can transmit in longer infrared wavelength regions. Also, there are phosphate glass fibers which can be of more highly doped with laser active rare earth ions. Radiation resistant fibers are made from materials which are you can say less affected by radiation and used, for example, in space application. Also, we have active fibers as a specialty fibers, which is being doped with laser active ions, generally with rare earth ions, are often generally regarded as specialty fibers. We also double clad fibers having an additional larger waveguide structure for pump light are even more special. Some fibers exhibit extreme or specially tailored parameters, for example, such as an unusually large fiber core diameter or a very high numerical aperture. Also, there are LMA fibers, I mean to say large mode area fibers exhibiting particularly large fiber modes. We can also have a fiber where the waveguide function is not obtained simply with a somewhat increased refractive index in the core, like step index fiber, but in some other complex way. For example, there are, we know, photonic crystal fibers, which is having periodically structured holes, arranged holes, and also called as holy fibers, which have quite complex propagation characteristics and structure. Another is polarization maintaining fibers, which is of having different designs can be used to maintain linear polarization state over arbitrarily long propagation distances. We do also have tapered fibers, which has been distressed to obtain a reduced fiber diameter, which usually changes along the length. They can be used, for example, for mode field diameters. So let's come to the long period grating inscription technique and optimization. What is actually long period gratings are in-fiber devices which consist of periodic longitudinal perturbations of refractive index and or the fiber geometry along the optical fiber that promotes the coupling between the fundamental guided core mode and co-propagating discrete cladding modes at some resonance wavelengths, due to which the transmission spectrum of long period gratings gets characterized by having a discrete attenuation bands. So these bands are positioned at resonance wavelengths along with satisfying the phase matching condition. So you can see here said that it's an in-fiber device that detects changes in SRI, surrounding refractive index, strain and temperature, and can be efficiently applied as a physical, chemical and biological sensor. So we can say that long period grating shows its credibility of being one of the most promising candidates to be employed in several chemical and biological application due to its intrinsic property of sensitivity to SRI changes, and others too. So long period gratings, whose length typically lies in the range of 100 micrometer to 1 mm, are inscribed by inducing a periodic longitudinal perturbation by acting on the refractive index of silica and on waveguide geometry along the optical fiber core. There are different techniques which have been employed to inscribe LPGs, the most important being namely UV radiation, mechanical microbands, ion implantation, CO2 lasers, IR femtosecond lasers, and electrical arc discharge. For our work, we use electrical arc discharge technique, which has gained much importance in the recent years due to having a property of being flexible, economical, and simple instrumentation, since it eliminates the need for expensive laser systems as well as removing the need for pre-hydrogenation of the fiber and consequent post-thermal annealing to stabilize the gratings. Actually, it creates the perturbation by applying an arc discharge to the fiber with a specific periodicity. There are several inherent effects arises during the arc discharge mechanism while inscribing the grating, namely we can say dopant diffusion, stress relaxation, geometrical deformations, and changes in glass structure. So the predominant effect prevailing in the arc discharge mechanism is depending on the writing condition and the type of optical fiber we use. So the most appealing feature of the electrical arc discharge technique lies in its intrinsic property to inscribe gratings in all kinds of optical fiber. In recent years, this technique made possible the long period gratings in various optical fibers like nitrogen doped and sulfur doped fibers, aluminum doped and aluminum erbium co-doped fibers, pure silica core and radiation resistant fibers, erbium doped and phosphorus doped fibers, polarization maintaining and microstructured fibers, etc. etc. So apart from the appealing features of EAD technique, of course, every method has some pros and cons. So the difficulty in the description of LPGs with smaller spatial period makes its most important limitation, that is a difficulty in achieving higher cladding mode order, for which the great efforts are being done since recent years. So we can see here the operating principle behind electrical arc discharge technique. We can see here in the figure that it involves a certain stripped section of an optical fiber positioned between the two electrodes. During the entire process, one end of the fiber is firmly fixed on a remotely controlled precision translation stage, while the other end is kept under constant axial tension, ensuring the straightness of the fiber between the electrodes to maintain an even power distribution on the whole length of the fiber. So in order to create the perturbation, the arc discharge is applied to a specific section of an uncoated fiber. So during the process, the electrodes are supplied with an electrical current of the order of few milliampere and a duration of hundreds of milliseconds. So you can see here the fabrication platform in an inset, like it's a state-of-the-art computer-assisted step-by-step inscription platform for long period gratings. We can see here that two electrodes are fixed by customized holders. It's electrical near the electrode holders mark you can see here. It is arranged on separated XYZ manual micro strippers, allowing high degree of freedom towards alignment of the fiber and the electrodes. Moreover, two customized holders kept at a distance of 20 cm kept the optical fiber suspended between the electrodes. So all setup was designed to permit the fabrication of gratings without creating any bending in the fiber during the process. So the electrodes are electrically connected to high voltage supply provided by commercial fusion splicers. So you can see here the wire coming from the splicer to the holders, to the electrodes. And the selection of the power and duration of the electrode supply current as well as the axial tension of the fiber allows the control of the modulation strength and thus the LPG spectral features, which is the most important aspect of getting the very good transmission spectrum, as you can see here in the inset, transmission spectrum versus wavelength. The typical values of the splicer parameters for producing effective discharge expressed in terms of arc power in the range of 1 to 20 step and duration of 200 to 800 millisecond. Generally, a constant force of about 120 millinewton was applied to the fiber by using a 12-gram weight and a high precision pulley. So we optimized for standard 28 fiber. So we can see here that for different grating period, we achieved more or less around 35 decibel, and we achieved low insertion loss less than 0.7 decibel, and also coupled to higher order cladding nodes up to LP08 as we go down, as we approach to the lower order period. And also the most important is we achieved the shorter length of the grating. It's like more or less around or less than 3 centimeter. So you can see also here the inscription of LPGs in specialty fibers, different kind of specialty fibers like RBM doped fiber, which is being used as a gain flattening in signal processing as radiation dosimetry. So we achieved more or less a very good spectrum, transmission spectrum approaching around 30 decibel. Likewise, in phosphorus doped fiber, which can be used as a radiation dosimetry. So we achieved a very good spectrum approaching more or less around 35 to 38 decibel. Likewise, pore silica core, it can be used as a radiation hardened sensors in space application, and also for photonic crystal fiber, like for both solid core and hollow core. Not really well, but it is acceptable. The transmission spectrum is acceptable for sensitivity purpose. So it can be used as also ultra sensitive chemical sensing and biological sensing. So for the characterization approach aspect, multi-parameter characterization, that is surrounding refractive index, temperature, and strain sensitivity. So we tried with Newfern and photonic crystal fiber and put it under these characterizations. So we achieved for Newfern that for SRI, as you lower down the grating period, the sensitivity, you will get the higher sensitivity around which we achieved around 55.72 nanometer per RIU. So it can be used in biochemical sensing. Likewise, in temperature, you can see for photonic crystal fiber, it is almost negligible, very less sensitivity, like plus 4.6 around and picometer, and for Newfound it is quite considerable, significant sensitivity around plus 30.0 picometer per degree Celsius. So in strain, you can see it shows more or less negligible strain sensitivity, but it is very much useful for cross sensitivity compensation. So you can see here for Newfound around 445 micrometer grating period, we achieved around 0.73 picometer sensitivity, and for photonic crystal fiber it's like minus 2.0 picometer, so it's almost negligible for both of them, so can be used significantly for cross sensitivity compensation. So if we talk about future prospects and challenges, so we would like to have even more higher and higher sensitivity. So we are working towards increasing the sensitivity by different approaches, by using long period gratings in such kind of specialty fibers. And also we would like to have some innovative optical fiber which is having some different kind of properties till now existed. And also we would like to have a broadening of a long period gratings application domain into other fields too. And also for the current scenario, we'd like to try for the detection and monitoring of COVID-19 molecules by using this long period gratings, by using any kind of fibers like specialty fibers or standard fibers with dopant, different kind of dopants, or also with different kind of coatings. So we will see. So thank you very much for your attention. Thank you very much.